Alright. How's everyone doing today?
No, exacto. Bueno,
Just a sec, actually, sorry.
pues yo no. A los pocos días yo sí. A los pocos días yo sí. Eso fue como el segundo semestre que estuve aquí. Nos vamos a Ana y yo testé antes de strep. Y le digo, vale. Le digo, ¿qué pasa? No, porque si tengo el strep, probablemente yo estoy teniendo nada.
Alright. What's up? Any questions before I get started? Alright. Well, today is Friday, March 25th. I've been saying that wrong all day. The chapter 5 homework and quiz I've actually pushed back to Monday, April 4th. Reason being it involves some chapter 6 stuff, so I'm just going to make it all one assignment. Let's do chapter 5 and 6 together. I'm just going to make one assignment to do with that later date. So that due date has been pushed back. This week, today we're going to continue on with the pressure stuff. We're actually going to begin talking a little bit about the flow of liquids and how pressure is involved in that. And that'll continue into next week. 2 weeks after that, we'll talk about heat and thermodynamics. And just to go ahead and keep it on your radar, test 2 will be in about a month, probably second to last week of April. It'll work very much like it did before, but and I'll make sure to, I'll finalize everything in the near future, and there'll be practice materials as we get closer to it, but just to keep on your radar. For right now, unless there's any questions, we're going to continue talking about Pascal's principle, which was, this formula, F1 over A1 equals F2 over A2. Talked a bit about what this formula represents, the idea that if you exert force on some surface area of a liquid reservoir, the liquid itself that you're pushing away, basically, will flow to another part of the reservoir and exert some amount of force on some other surface area of the tank. The example that I've been showing you to help visualize this was the water reservoir at the bottom of a hydraulic system. Some piston pushes down on this part of the system, pushing fluid through this pipe. That fluid flows through the reservoir, to the other side, where it will push upwards on a different piston. This happens because liquids can't be compressed, or at least they can't really be made smaller under pressure. You can't really squeeze water and expect it to shrink. It's just going to flow away from you. Whereas if you squeeze a gas hard enough, it will actually shrink and compress into a higher density gas. So this is entirely based on a few properties of liquids. You can kind of use gases in a similar way. That's called a pneumatic system. But we're going to talk about hydraulics for right now, the liquid version, because the fact it doesn't compress makes it easier, frankly. So, formula says F1 over A1 equals F2 over A2. The force you apply on one side will partly determine the force that comes out on the other side. The surface areas of, say, these two pistons also matter. The cross-sectional area, like the flat surface area, is actually touching and pressing into the relevant liquid. Now, we haven't used this formula yet, so I have a few quick rapid-fire concept questions before we actually do the math for the actual car lift picture that I showed you last time. So real quick, I'm actually going to rewrite the formula over here. Let's use the same basic physical setup as the picture we've been showing. The same two-sided reservoir with two pistons. Let's say that on piston 1, we exert 1 Newton of force on a 1 meter squared piston. How much force do we get out the other side of the reservoir, out of the other piston, if the second piston's area is also 1 meter squared?
1 Newton.
1. It's not a trick question. If you plug in all ones, you'll get all ones back out. So in this situation, when the pistons are the same size, the force you put in is the force you get out. You're basically just sending force from one side to the other. This alone can be pretty useful if, say, all of your machinery is in one place, but you need it to work somewhere else. You can set up hydraulic pipes, and you can send force from one side to the other. Pretty useful. Where this gets more useful is if you start changing the sizes of your pistons. What happens if the second piston, instead of being 1 meter squared, is 2 meters squared?
2 Newtons.
You'll get 2 newtons out the other side. So you've actually increased the force from one side to the other. What about 3 meters squared? 3. This machine has the potential to just multiply the force you put into it. That might seem too good to be true. It is true, and there is a drawback. Every machine has some flaw. I will talk more about that drawback later. For right now, the main thing I want you to keep in mind is hydraulic systems like this can send force from one place to another and multiply it based on the ratio of the sizes of the pistons, which is really, really useful. Because as we'll see in a second, cars are heavy, and it's nice if you're able to lift them with less force than they weigh. Last quick rapid fire question. What's the pressure acting on all of these pistons? What's the formula for pressure? If you recall? Force. Yep, force over area. So, well, the first piston was 1/1, so that's 1 Pascal. The 2 meter one was 2/2, so that's still 1 Pascal. And the third one's 3/3, so that's still 1 Pascal. The reason we call it Pascal's principle, and we've only ever used the term Pascal to refer to, the unit of measure Pascals, the unit of pressure, is because literally you're comparing the pressure on one part of the system to the pressure in the other part of the system. The force is changed, the area is changed, but what the machine actually does is it just sends completely the same value pressure from one side to the other. Whatever pressure you exert on this piston is the same pressure that will be exerted on the other one. So you can view this as pressure being the real thing that you're sending from one side to the other. If you press on a fluid, the fluid will press back. Questions so far? All right. So, I showed you this image before. We've been using it as a demonstration of this concept and as a place where you would have seen it before, or possibly seen it before. Let's put some numbers to it now to kind of get a scale for what it would take to actually lift this car in this way. So, we have our 2-piston reservoir system. We now have sizes for each of those pistons. The first piston, the smaller one that we are going to ourselves be pressing on, is 25 centimeters squared as its cross-sectional surface area. And the second piston is 2 meters squared for its cross-sectional surface area. So, keeping in mind that these are not the same unit, we're comparing centimeters squared to meters squared. One of these pistons is much, much, much smaller than the other one. The one that we are acting on, A1, is much smaller than A2. Centimeters squared are 10,000 times smaller than meters squared. So these are very differently sized pistons. The one we're acting on is the smaller of the two. And we need to figure out how much force we need to put into the left side in order to successfully hold the car into the air on the right side. Now I want to give you guys a couple of minutes to work on your own or amongst yourselves. There's a couple of catches that I want to see if you guys can recognize on the journey to getting the final answer, and we'll compare notes in a minute.
Should we be converting meters to centimeters or centimeters to meters? Or is that something that you want us to also figure out?
I suppose as long as you convert one to the other, it doesn't matter which one, but I suppose the good metric answer would be to convert the centimeters squared into meters squared. Because that's the standard unit that we tend to operate in. But yes, that is a conversion you will have to make. All right. Does anyone have any final answers to submit before we compare notes? Bless you. All right. Well, let's do it together. So we have our two areas. That's nice. We want F1. We weren't given a value for F2, but we will be able to approximate one in a minute. First, let's look at the areas though. Whatever unit they are, they do need to match. Because the way the formula works, we have F over A equals F over A. Technically speaking, it doesn't really matter what unit for area you use as long as the two sides are the same unit. So we need to convert either meters squared into centimeters squared or centimeters squared into meters squared. I'm going to convert centimeters squared into meters squared real quick, and I will remind you that there is a small catch when doing so. We can use our conversion. There's 100 centimeters in 1 meter. Will this convert centimeters squared into meters squared on its own, though?
No, but it'll cancel out centimeter.
Correct, because centimeters squared is not centimeters times something else, it's centimeters times centimeters. So just dividing by centimeters once doesn't cancel out the other one of the two. We have to do the conversion twice. So it is 25 divided by 100 equals 0.0025 meters squared. Again, you need to do this every time you're converting something that is either squared or cubed or etc. Because just doing it once, the conversion's not done, you have a weird incomplete unit.
Yes.
So, this is the actual meters squared surface area of cylinder 1. It's very, very, very small. There's a centimeter. If it seems too small, I will point out to you that, bless you, 1 meter squared is 1 meter by 1 meter, whereas 1 centimeter squared is a centimeter times a centimeter. So, it takes 10,000 of these to fill up the bigger one. So, we have our two areas converted now. F1 over 0.0025 equals F2 over 2. We do need, if we want F1, we do need some force to plug in for F2. How much force is required to hold a 650 kilogram SUV in the air?
A lot of force.
A lot of force, you are correct. Specifically, to hold anything in the air, you have to exert a force at minimum equal to its weight. You need to work hard enough to cancel out gravity and keep it from falling. So, we can approximate F2 as being the car's mass times 9.81. Specifically, we need to generate enough force to cancel out its weight. So, we will plug in the value for its weight. Why do I keep closing this marker if I just need to open it again? I'm going to show my algebra steps because I feel like I haven't been doing that enough lately. F1 over 0.0025 equals, these two things multiplied is 637.6.5 over 2. Go ahead and do that division, which will give us 3,188.25. And then we multiply both sides by 0.0025. And that should give us a final answer, approximately, of 7.97 metric newtons. Does anyone disagree? Yes.
So why is the 25 centimeters squared converted to?
So we do need the two units to match. I just chose to turn centimeters squared into meters squared. In order to do so, we have centimeters squared, we want meters squared. In order to cancel out centimeters in our conversion, we need to be dividing by the centimeters part of the conversion. And there's 100 centimeters in 1 meter, but we have to do it twice because it's centimeters squared. If we only divide by 100 centimeters once, that only cancels out half of the centimeters squared part, because centimeters squared is centimeters times centimeters. And so 25 divided by 100, and then a second time divided by 100. Does that help? Okay.
Wait, hold on. How did you get 7.5 meters again? How many 7.97 meters again?
So my first step, multiply 650 by 9.81. That gave me 6,376.5. That is then divided by 2, which gave me 3,188.25. So F1 over 0.0025 is equal to this. We can then multiply both sides by 0.0025. So 3,188.25 times 0.0025 gave me 7.97. Yes.
Alright, so I cross multiplied
Okay.
like that, but I got like a lower number by 1. Do I have to count it off by that?
How much lower?
Like 7.962.
Oh, that's fine. That's probably just a result of me using all of the sig figs my calculator gave me and keeping them all the way through. Like that's, you said it was 7.96. That's fine. That's reasonable. I wouldn't worry about that. That's literally 1% off. And I don't write it that way. But is anyone more than 1% off from this number? All right. Now for a sense of scale, because even I have a hard time thinking like what does a Newton mean some days, that, approximately 8 newtons, is about 2 pounds. So you could lift this car and hold it in the air with 2 pounds of force.
Put a baby on there. No.
I wouldn't recommend it, but you could, I mean, why not just set these on it? But yes, you're right, it's not a lot of force. So that seems kind of amazing, and it is pretty amazing. I will now tell you the drawback of this machine. Because this is a machine that multiplies force, which is a really cool thing. It's why we use these things. The downside is, this isn't a machine that necessarily just multiplies force magically. This is a machine that sends a volume of liquid from one side to the other. As you press down on this side, some amount of water exits that cylinder, travels through the other part of the reservoir, and goes into the other side. So if you push 1 gallon of water out of tube 1, tube 2 will rise by 1 gallon. But each tube is a different size. The one on the left, by virtue of the fact that the piston is really, really small, is really, really narrow, whereas the one under the car is gigantic. Which means that if I push down by 1 meter, just as a sample, if I push down on this by a distance of 1 meter, that volume of liquid is not going to raise this side by 1 meter. It's like expecting 1 full coffee cup to fill 1 full pool. It's just not going to work. And so the picture does try to demonstrate this a little bit. We didn't use any delta X in our math. We didn't need to. But what this is here to show is it would take pushing down on this cylinder by this much to get the other side to rise by this much. So the downside, the drawback to this machine is, since you need to move, you need to move enough fluid into this cylinder to fill it completely and raise the water level up to where you want the car to go. And in order for a cylinder this wide and that tall would hold, gallons of water. For a cylinder this narrow to hold the same volume of water, it would need to be 10 stories tall. So that's the drawback. You would have to exert 2 pounds of force and push, 10 stories worth of water down a pipe in order to get the other side to rise that much, just because of the volume difference. The area difference. Still useful. The machines just have to find a way to work around that. Usually they just bend the pipes so that they fit in the basement of the building. instead of just one straight pipe that goes up into the stratosphere. And usually the area differences aren't quite this extreme. Still useful, just a quirk you gotta work around. Questions? All right. So, in talking about this, we've kind of introduced the concept of flow, the flow of a liquid into the math that we've been doing. Because for this machine to work, there's a liquid under here. It has to flow from one cylinder to the other as you exert pressure on it. Water flows because of water pressure. When you turn on a faucet, there's water pressure inside of the pipes that literally forces water through them and to come out through the sink nozzle. Liquids and gases, really all fluids, are capable of flowing because while liquids have definite volume, they don't have definite shape. You can take like 1 meter cube of lead versus 1 meter cube of water, that mass of water can all flow through a hose, but the giant cube of lead won't because its size is predefined, its shape is predefined. Liquids, gases, they can flow, that's why they work in this. And pressure is what causes them to flow. How they flow depends on, one, the pressure causing them to flow, but also what they're flowing through determines how they flow. And so we're going to start adding on to the math we just did with a few new, well, we're just taking it one step for right now. So this is the immediate next step. We looked at liquid flowing from one part of the reservoir to the other because of the pressure put on it. Pressure is what causes that flow, and now we're going to look at what determines the rate of flow. Now, there's a formula here, there's an explanation for that formula. Before we focus too much on this, I want to draw your minds to a specific case where you've seen this concept before I start addressing the math. Envision a garden hose, the kind just connected to the side of a house. You crank the nozzle and then water starts coming out the other end of the hose. Pressure, water pressure, is what's pushing that water through the hose, and it's able to flow out at a specific speed based on the cross-sectional surface area of the exit nozzle. The bigger the nozzle is, the more water is able to fit through it more easily. But when you turn on that garden hose, and it doesn't have a handle connected to it, it's just the metal nozzle with just water coming out. It tends not to come out super fast because you don't want the water pressure in your house to be super high. But say some member of your family or some other person that you grew up alongside took that hose and covered part of the end of it with their finger. What happens to the flow rate of the water?
It shoots out farther.
Shoots out farther. Some family member or some person you've observed at some point in your life has probably done this to cause the water to either come out faster or to shoot farther for whatever reason. Car washing, gardening, antics. This formula is the reason that happens. When you cover the nozzle, you literally just put your finger over part of it. You've reduced the amount of space that water can occupy, which means all that water is now pushing and rushing even harder to try to get through the limited space that's now available. When you cover the end of the hose, you reduce the cross-sectional surface area that the water can travel through. You literally block off part of it. So now there's less space and the water's fighting to get through harder. By reducing that area, you drive up the speed of the water. And that's why that trick works the way that it does. this is the math, the physics that explains that particular phenomenon. This formula is called the continuity equation, and it states that the flow rate through a certain pipe, as the area of that pipe changes, will determine the relative velocity of the fluid as it flows through that part of the pipe. If we look at this particular pipe here, on one side of it, it has a relatively small cross-sectional area, and it gets bigger further down. As that area changes, the flow rate will also change. Generally speaking, the narrower the exit, the faster the water will move, whereas the wider it is, the slower it will move, because, well, it's kind of similar to whether or not a bunch of people are trying to fit through a small door versus trying to fit through a bigger door. The smaller the door, the people are fighting, and they have to move pretty quickly to get through without getting elbowed. The bigger the door, people are able to walk through casually without any side effects. So, exits, the size of the exit determines the speed at which the fluid will flow through it. This is why the end of a super soaker is always very narrow, whereas the end of like a sewer opening, which you don't want to blast out at high speeds, is always very large. Questions so far? Okay. So, let's put a few numbers to that childhood garden hose story. Let's say that the hose connected to the building that you're living in, normally, where's my eraser? Oh well. I'm left-handed, my hands end up dirty anyway. Let's say that the garden hose attached to your particular dwelling in this example normally has a cross-sectional surface area of 5 centimeters squared, and normally, when unobstructed, the water flows through it at a rate of 1 meter per second. Someone then takes their finger, partially covers the hole, and as a result of that, the reduced cross-sectional area would look something like this. You've blocked the upper half, and now all the water is trying to blast out through that reduced crescent moon-shaped sliver. I don't have a formula for area of a crescent moon, but we'll figure it out through a different means. We don't know that new reduced area, but we do know that after doing this, the water now exits at 5 meters per second. Reducing the area has made the water faster. Any issues with the pictures I drawn?
What is the crescent supposed to be? How much is left after the thumb is covering the?
Yes. So if this is the original opening, imagine a thumb coming in and pressing and covering that much of it. The crescent moon is what is unobstructed. Does that help? Okay. So, we're trying to find the remaining unobstructed portion. This is the remaining surface area that the water is able to flow through. And it is flowing through it at an increased speed. We know that speed, and we know the original speed in the original area. So the continuity equation can tell us what that new reduced area is. And we're going to cheat a tiny bit here, because we were given the original area in centimeters squared. I suppose if we were trying to be as good metric scientists as possible, we should probably convert that into meters squared. But You don't necessarily need to in this specific case. I'm telling you this so that you understand basically how the formula works. The continuity equation is area times velocity equals area times velocity. It's the same units on both sides. If you put meters squared and meters per second over here, you'll get meters squared and meters per second over here. Whatever you put in is what you get out in terms of your units. And that means that you could hypothetically put in centimeters squared and miles per hour if you wanted to. You would just get centimeters squared and miles per hour out the other side. So technically, if you just need an answer using this formula, you don't necessarily need to convert it into metric because we're not calculating any new units, we're not dealing with constants that have some weird unit that interacts in a specific way. It's just, you get out what you put in. So if we put 5 centimeters squared into our formula, we'll just get centimeters squared back out as our answer. And which will generally be okay unless the homework service specifically says, put answer in meters squared. So pay attention to what unit Achieve wants the answer in. Generally speaking, you're always safest converting into standard form, but some people do notice this as a time save, and I didn't want to ignore it. So, for example, if Achieve asked you this question and asked for the answer in centimeters squared, you can just put centimeters squared in and get centimeters squared out. So, any questions about that long rant I just made? All right. So using the formula, we'll put 5 centimeters squared and 1 meter per second on the left. That means we will get some unknown amount of centimeters squared on the right, along with the 5 meters per second we're going to plug in for velocity. Again, this only works as long as every unit matches right to left. So 5 times 1 equals blank times 5. What's our final surface area?
1.
1. Not a trick. We've reduced the cross-sectional area down to 1/5, and as a result, the water comes out 5 times as fast. Nice, straightforward multiplication for once. And that explains why the garden hose does that thing that it did. This does show up in other places. This is a commonly used trick in really all of plumbing in order to control water pressure and flow rate. If you have water going into bigger pipes, it'll just flow slower, and then if you want it to flow faster, you direct it into smaller pipes. You may also notice this, you don't even need to cover the hose with your thumb necessarily, because most handle nozzles that you attach to garden hoses have different settings on them, kind of the very same way that a shower head has different settings on it. Most shower heads have a different number of holes that are each different sizes, and when you change the setting, you change which holes or how many holes the water comes out of. If there's more holes open, that's more exposed surface area, the water tends to come out slower. But when you crank it up to a faster setting, you tend to reduce the number of holes in use, and that means there's less open space, water comes out faster. So you've observed this before in some way, shape, or form, even if you never specifically saw the hose conversion. How do we feel? Okay. There is actually only one more pressure-related topic before we actually resolve the chapter 5-6 combo stuff. But the last formula is a bit of a doozy, and I don't like holding people up or scaring them on Fridays. Does anyone want out of morbid curiosity to see the last formula? All right, we got at least one yes. Here we go.
Hostia.
What?
I told you.
It's like, algebra.
Momentum.
It is algebra. It's quite literally algebra. Like I said, it's a doozy. We'll talk about what it means next time. This formula is like literally the culmination of all of the pressure and flow stuff from the past week rolled into one. But it's Friday. I don't want to scare you before the weekend, and I let the other class out early, so we'll do the same. Any questions before we break for the weekend? Keeping in mind, Monday, our task will be dissecting this thing. So be excited for that. Until then, if you have any questions about anything, let me know. I might see some of you later today. Some people are making a lap this afternoon. If I don't see you later today, actually, I'm rambling. Have a nice weekend.
Thank you.